So, see, aren't you glad you asked all these questions? Skipped over so many slides. So let's prove that the halting problem is undecidable. So far we proved that some Boolean functions are not decidable or not computable. They have no algorithms for them. But we didn't give an example. We're about to give an example. By the way, it's the case of diagonalization, in case it wasn't obvious. It's a non-existence proof. We proved we're not a millionaire. And another way of looking at this is these numbers here. You can think about it as real numbers. Put a decimal point here. And all these strings of digits are real numbers between 0 and 1. And all combinations of zeros and ones past the decimal point is all the real numbers between 0 and 1. How many can see that? And there's an uncountable number of those. But that's besides the point. Okay. So we showed that number of programs is countable, number of Boolean functions are not countable, which means some Boolean functions are not computable. There's no algorithms for them, no matter what. Okay. And then the halting problem is one of those things. Right? So the halting problem is given a program P and an input I, does P halt if we ran it on that input I? Right? So we make now two arguments into this predicate H. So H is a function from natural numbers to 0, 1, and it's the ith program and the jth input. You can sort the programs, you can sort the inputs. Right? And by the way, could you write a program right now that prints out all valid C programs? In other words, this list of programs here, could you write a program that prints all of these out in order? How many say you can do that right now in one afternoon or one evening? Write a program that prints out all valid C programs. How many say it can't be done? How many say you could do it, but it'll be a big, huge effort, millions of lines of code, trillions of lines of code, Okay. How many say you can do it in one evening? And you'd be right. Why? Describe to me a piece of code that prints out all valid C programs. And by the way, will it also print itself out? Yes, it will, because it is a valid C program.
Does it have input?
What's that?
Does it take?
No, it doesn't take any input. You start running it, and you start spitting out all these programs in order, in lexicographic order, just like on this list. How many can see how such a program would work? Only a few. Well, I'm glad I asked. A bunch of smart writers who. Yeah. If it's not obvious, then you should think about it. How would you do it? How would you write a program that prints out all valid C programs?
You can also print out all invalid programs, just prints
Good
out
question.
every letter.
Good question. No.
Okay.
Why? Let's talk about that for a second. He's asking, could it also print out incorrect things? Let's print out all strings. So you can't print out incorrect things. So when I ask you a question, you should not just give me the correct answer to that question. You should not give me any incorrect answers to that question. That part usually people don't even think about. But if you ask me, the stock market is going to go up tomorrow or down tomorrow, I'm going to say yes and no. And one of these two answers is right, and I gave you the right answer. How many see that? I just gave you the right answer. But I also gave you a wrong answer. I didn't tell you which is which. So I didn't commit any big feat of logic and cleverness. So that's why you should not give a wrong answer and only give a right answer. And that's why in a court of law, when you testify under oath, like Trump is about to do for Comey, for Mueller, I guess, they tell him to tell the truth, the whole truth, and nothing but the truth. And these are three separate things. And you see why they do it in a court of law. Just to say, tell the truth. And tell the truth plus a whole bunch of lies. And you told the truth, but also a whole bunch of non-truths. But nobody told you not to do that. But that's very important. If you're allowed to do that, your testimony is worthless. You make up all sorts of stuff on top of the 2 bits of truth that might be embedded in a very long and complicated set of lies. So, very good question. So, the program should give you the right answer and nothing else. Yes?
We know that a valid program compiles. So, enumerate every string into sigma star and run it through the compiler. if it does compile, spit it out.
Yeah.
And you
everybody,
get all
everybody
the-
see that? So it's easy to generate all possible strings. See that? You know, in lexicographic order: A, B, AA, AB, BA, BB, AAA, AAB. You know, just generate all strings in dictionary order, smaller size to larger size. Some of them will be programs, other will be gibberish. Some of them will be Shakespeare's Hamlet, the entire text of the play of Shakespeare's Hamlet. How do you understand that? And your entire textbook will be one of those strings, but all gibberish, random stuff will be some strings also. How do you know which are the right programs, the correct programs? Call the compiler on each. The compiler says, okay, compile without any errors or warnings. Print it out. If the compiler complains, move on to the next string. Don't print it out. That's a very simple scheme. It's just a few lines of code plus a call to the compiler. That's it. That's the entire, and you can certainly do that in an evening. How many see that? Okay. So that's very easy to generate this list algorithmically. And one of the programs that this scheme will spit out is itself. There's no contradiction there either. It will come up in this long list of strings in order, and it will compile, and it will print itself out along with many other valid programs, and it'll print no invalid program. No gibberish, no Shakespeare's Hamlet. Okay, any questions so far? Yeah.
What if the compiler doesn't fault, or does it have to?
We're assuming the compiler does its job. We assume there's no bugs in the compiler. So, compiler ostensibly should take a program, print out any syntax errors that he cares to, or warnings that he wants to complain about, and then stop it and say, I'm done. Or it should compile without any warnings or errors and be done again. Either way, it ends. The compilation process ends. No compilation process should run forever. Otherwise, the compiler has an error in it. Let's not worry about errors in the compiler. Just like if you say, A plus B, you don't worry that the addition operator is implemented erroneously or wrongly. When you talk about addition, you assume the addition works. So you assume when you say about compilation, you assume the compilation works. It's just not an operator. It's like addition, it's like operator.
So will the compiler be considered part of the program?
You could say that, yeah. So if you want the program to be complete, take the entire code of the compiler and stick it right in there. All 10,000 lines of it. Or you can subroutine call and implicitly include it by calling the subroutine call. Either way, we completely describe this algorithm. And it's pretty straightforward. It's no more complicated than a compiler, plus a few extra lines of code. Run the compiler and then the string. So far, so good? Okay, so just so we know that that's possible. Okay, so we already know that some Boolean functions cannot be computed, so let me show you why halting intuitively, why halting is so difficult. You might think, here's a program, does this halt? Yeah, of course. It doesn't do much, it doesn't cycle, it doesn't move, so of course it halts. Here, I can show you this program, this runs forever, right? While true, begin, end, yeah, this will cycle forever. So why is halting so hard to determine? Why is it so difficult that no algorithm can possibly do the job correctly for all programs? Well, one reason is because programs would be large. The Microsoft Windows Vista or Windows 10 or whatever the latest operating system is, does that halt? Well, it shouldn't, but it sometimes does. How many realize that an operating system sometimes crashes on you? It happens too often than we care to admit. And if Microsoft could actually make it not halt, that would be amazing, right? I mean, that's in fact most of their business is to make their programs operate not halt, not crash, right? But it's very hard to do. Sometimes your smartphone crashes, and it shouldn't. And the reason it's so hard to get an operating system not to crash is because it's 100 million lines of code. It's hard to get 100 million lines of code to be all correct. On average, there's a bug every 100 lines or so. So you have 100 million lines of code, there's probably a million bugs in it. Even really, really good programmers make at least one mistake every 1,000 lines of code. So 100 million lines, that's 100,000 bugs in an operating system. That's a huge number. It's hard to avoid it. So size It makes it hard to determine halting or not halting. But there's a much more subtle, much more fundamental, much more insightful reason than that. It's not just size. Size matters, basically. It's not the main reason. Let me show you why it's so hard to determine whether a program halts or not. Really, why it's really hard. Here's a small program that finds a Fermat triple of the form a to the n, b to the n, added up together equal to c to the n for a, b, and c. So it's a triple loop that finds a's, b's, and c's, and n bigger than 2. So it dovetails through all a's, b's, c's, and n bigger than 2, and tries to find a triple like that. And if it finds it, it prints it out and stops. If it doesn't find one, it keeps going, because there's an infinite number of combinations of a, b, and c in there. In integers, a, b, and c, and n. Will this program halt? It only halts if it finds such a triple with n bigger than 2. How many say it will halt? How many say it will run forever? Good. How do you know that? Because Fermat's last theorem has been proven. So this will run forever, but this was, whether this small piece of code will run forever or not was open for 3.5 centuries. Humanity couldn't figure out if this piece of code will halt or not halt for 3.5 centuries. It's equivalent to Fermat's last theorem. How do you understand that? So it doesn't halt or not halt because it's very large and there's too many lines of code and nobody can program that many lines of code with accuracy without any bugs. No. How many lines of code are we talking about roughly? Give me a rough order of magnitude. How many lines of code is this roughly? How many say they can code this in a day? Yeah. How many lines of code are we talking about? A few dozen at most. Not even 100. It'll be like 20, 30, however long it takes you to go through a triple, quadruple loop, I guess, and dovetail through all these values, increasing maximum order of any of them, and search the entire space. 3.5 centuries to determine whether 10 lines of code will ever halt or not halt. A proof or this proof. And the proof was hundreds of pages long for these 10 lines of code. You see what's going on here? Let me show you another example. The Goldbach conjecture. Goldbach conjecture says that every integer, every even integer, is a sum of 2 primes. So for example, 12 is 5 plus 7. 5 is prime, 7 is prime. Add them up, you get 12. 20 is the sum of 2 primes. 13 plus 7 is 20. Now it turns out that some even numbers are the sum of 2 primes in many different ways, not just one, but at least one way to present every even integer as a sum of 2 primes. How many heard of that conjecture? Okay. How many say it's true? How many say it's false? How many say it's an open question? It's been open for 150 years, actually 250 years plus. Open since 1742. So here's a small piece of code that goes through every prime number and tries to represent it as a sum of 2 primes. Every even number as a sum of 2 primes. So it tries it for 2, for 4, for 10, for 12, for 14 in increasing order. And for each one of those, it tries to find 2 primes and add up the number. And if it ever fails to find, if it ever finds an even number that fails to be representable as a sum of 2 primes, it will stop and raise its hand and say, Eureka, I found one counterexample. We don't know if this program holds or not. It's all, how many lines of code are we talking about? Again, roughly. 10, 15, 20, depends how thrifty you are. Code. We're talking about 10 to 20 lines of code here. So we have no idea if it holds or not after 2.5 centuries of thinking about it. Almost 300 years. And if you can figure out if these 20 lines of code hold or don't hold, probably get a Turing Award. Certainly you get the fields medal in mathematics. Question?
Yeah, what if in the future we discover all there is in the mathematics and we can check if the loop is infinite or not?
So the point of this is that whether it holds or doesn't hold is open conjecture. It's been open for a long time. So what I'm telling you is that you can take arbitrarily deep mathematical statements, conjectures, and embed them into relatively short pieces of code whose halting status will be equivalent to the truth of the conjecture, and conversely, whose non-halting status will be equivalent to the falsity of the conjecture. And proving one will be the same as proving the other. How do you understand what's going on? And so it's not about size. Size certainly doesn't make it easier to determine halting, because it's too complicated and hundreds of millions of lines, billions of lines of code. It's not going to make it any easier. It's certainly going to make it more. But that's not the reason. This is the reason, right? That's the more subtle reason. Because an arbitrary mathematical statement can be embedded in very short whose halting, non-halting status is equivalent to the truth and non-truth of those conjectures. And some of them have been open for centuries. There's a huge incentive to determine whether this 10-line program halts or not, or this 15-line program halts or not, and we don't know. And it's just 10 lines of code. There's something very subtle going on here. So the halting, non-halting status of a piece of code is equivalent to arbitrarily deep and convoluted mathematical truths and conjectures and possibly theorems that we don't know how to resolve. And so we certainly can't resolve halting in general, because halting is even more general than mathematical conjecturing. You can embed physics questions in pieces of code. Determine, all sorts of deep quantum mechanical physics questions as simulations and see if they're consistent or not as a relatively short piece of code. And whether it halts or not will determine if physics is consistent, if your theory of physics is consistent or not, or whatever. You see, that's the crux, and of course size doesn't help with complexity, but it's not. But that's not the issue. How many knew this before? Well, my gift to you. It's good. Now, that's an intuition why solving halting or non-halting is so difficult. That's not a proof why it's difficult. It's an intuition. Here's a proof. Not this one. This one. So here's Turing's monumental result that surprised all of humanity. We had no idea that this could even possibly be true. So the halting problem is not computable. How do we prove that? So assume towards contradiction there's an algorithm that solves the halting problem, and call it S, some subroutine that takes in a program and an input. There's two parameters. Yeah, you can do that. And then it determines whether that program will halt on that input if it ran on that input. And the answer is either yes or no, either case. So either it says yes or no, and either way it stops. And it's always correct. So you're not allowed incorrect responses. Right? So I deliberately wrote it as a black box, call it S. Because I don't want to talk about what's inside, because if I start splitting hairs about what's inside, you'll say, well, the result only holds for programs that has that structure inside. So I allow it to be anything it wants to inside the box, as long as it's a program or an algorithm, a finite set of instructions. Loop as much as you'd like, but at the end, stop and say yes or no. I'm about to show you that no such S can exist as an algorithm. That would be the result. It'll all fit on this one slide, so it's not very long, but it's subtle. And it's not obvious, and it's pretty weird. All right, so I'm going to take this subroutine here, make a copy of it, and use it in a larger subroutine called T. And this larger subroutine will use S as a subroutine. This larger, script that has S embedded as a subroutine call. T has a formal parameter X. And by the way, P and I and X are all integers. Right? Without loss of generality, I can represent a piece of code as an integer. Why? Because you can enumerate them in canonical order by size within size by dictionary order, number them all. And when I say joke number 23, all the prisoners will know what the joke is, right? Because we all agree on the canonical ordering of the jokes. Right, so all the programs could be sorted in integers, and all the inputs could also be represented by integers too. Because a program is a string, an input is a string, and those are equivalent to integers. But that's besides the point. So in comes in the parameter X, it's an integer, and I'm going to feed it into S as both P and I. Right, so T will take its input X, whatever that is, and feed it into S as both P and I. Make a copy of X and feed it both as formal parameter P and formal parameter I into S. And then S will determine whether P will hold on I and say yes or no. P will watch what S is doing, what it's outputting. After finite time, S will output either yes or no, always in finite time, always correctly, right, by assumption. Towards contradiction, we're assuming that S exists, always does its job. But if T sees S coming up with a yes, he will deliberately go into an infinite loop. if t says that s says no, it will immediately stop. That's all t does. It calls s once, and based on what s returns, it does either an infinite loop or a hard stop. How many understand what t does? Very simple. Now ask yourself, if you feed t into t, what would happen? Feed t to itself. By the way, could you feed a program to itself as input? Of course. The program takes in a file as input. That file could be its own source code. You know, what will happen is a different question, but you can certainly do that. The universe will not implode on itself if you do this. Right? The question is, do you want to do this, and what would happen if you do this, and why would you want to do it? That's a different question. But technically, feed a program to itself. In fact, you can feed a program anything you want, not just itself, but itself is a special case. So if t is fed to itself, x will be equal to t, because you're feeding t here as x, as the formal parameter x. So p will be equal to t, and I will be equal to t. And s will be asking what p does on I, but they're both equal to t. So s will determine what t does on t. How many see it so far? Okay. And if t on t will halt, s will say yes, and t will immediately go into infinite loop and not halt if t on t halts. So if t on t halts, t will go into an infinite loop and not halt. On the other hand, the only other alternative we can save us is if t on t does not halt, and if t on t does not halt, p will be equal to t, I will be equal to t, same as before. S will determine that t on t does not halt and say no, in which case t will see that no and immediately stop and halt. So if t on t does not halt, t on t will halt. That's a very bad day, because now we have a logical computation. We have something in the form q if and only if not q. T on t will halt if t on t does not halt. That's a contradiction. So one of our assumptions was false, because this clearly cannot happen. T on t cannot halt and not halt at the same time. That's a contradiction. So what assumptions did we make here along the way? Well, we assume that S exists, always does the job. We assume that if S exists and does its job and always halts correctly, we can take some parameter and feed it to S, that you can take a yes output from S and make that into an infinite loop. This is a couple lines of code. You know, if this is equal to yes, then while begin and, you know, while true begin end, that's an infinite loop right there. It's one line of code. You can convert a no to a stop, to a hard stop. And, the only assumption that's not trivial is that S solves the halting problem for every pair P and I, and does so correctly within finite time. That's the only thing that's not obvious. It's not obviously true or obviously doable. And what did we assume about the inside of S, the inside of this black box? Nothing. We didn't assume it was in C or Java. We didn't assume it uses arrays or data structures that are pointer-based. We didn't assume it uses a database to support it, how it works. We didn't assume that it's running on Unix versus Linux versus Windows. We didn't assume that it's written in machine language or not. We didn't assume that it's less than 1 billion lines of code or more than a Google lines of code. None of that we assumed. Just that it's an algorithm in there, a piece of code of some kind, doing some thing. We gave the inside of S complete freedom of how it wants to be and how it wants to behave, as long as it does its input-output job correctly. Which means no algorithm in the universe can possibly sit inside this black box and do its job. How do you get that? That's the proof. That's a monumental discovery. It's one slide, it's not long, but it's very subtle and it's very weird. And this is an instance of diagonalization, if you think about it. How many can sort of smell diagonalization here? Okay, think about that, meditate over that. It's an instance of diagonalization. And sometimes I like to represent it as Pinocchio saying, my nose will grow now. It's Russell's paradox. Diagonalization is a version of Russell's paradox. You know, Pinocchio's nose grows if and only if Pinocchio is lying. Right? How many heard that? Okay. So if Pinocchio says, my nose will now grow, if his nose will grow, actually, he's telling the truth. So if he's telling the truth, he's not lying, so his nose should not grow. But if its nose is not growing and it says it will grow, is lying and it should grow. So Pinocchio's nose will grow if and only if it will not grow, which is another contradiction. So this is in cartoon form what's going on here. Russell's paradox. And we skipped over Russell because we skipped over 300 slides, but that's okay. You asked, and here we are. We'll get back to Russell. So it's a non-existence proof. We're proving that something doesn't exist. What doesn't exist?
The solution to the halting problem.
A solution to the halting problem in the algorithmic form. Very important, because there's plenty of solutions to the halting problem that are not algorithmic. And there's Turing smiling, and Cantor is smiling too, because it uses diagonalization very heavily here, which is Cantor's gift to us as a human race. So Turing built his work very, very heavily on the back of Cantor's results. And that's why I introduced Cantor first, and this is the situation. So any questions about this? It's not long. Anything that fits on a slide, a single slide, is by definition short, right? But it's one of the most surprising mathematical results in human history. That there can't possibly be an algorithm that solves the halting problem, even though it's completely well defined. We know exactly what a piece of code is and what a piece of code isn't. That's what a compiler is. We know exactly what it means to halt or to not halt. There's no in between. It's very unambiguous. The program either halts or it runs forever. There's no in between. Yet, this cannot be determined, even though it can be precisely stated. Question?
We are describing something which is an algorithm, but if it is an oracle, even then it should not be possible.
Okay, we'll talk about that in a second. All we're saying here is that there's no algorithm inside the box. That there's no possible way for some algorithmic behavior to be encoded in this box as a piece of C code or Java code or any other piece of algorithm or algorithmic mechanism. What we're not saying is that this box cannot contain magic or a little gnome, you know, or elf, like from Lord of the Rings or whatever, some magical creature that somehow divines the right answer. That's not, we're not saying that.
But even then, it shouldn't be possible.
No, it should. It can. There could be a magical creature that divines the answer every time. Correct.
So in such a case, then they will. In the previous slide, we tried to explain that that is possible. Correct.
So there could be some, Harry Potter magical creature, some magic spell kind of, that somehow divines the right answer every time, not algorithmically, by magic.
They can't take in itself as input in that case. Because it only takes input, in as input programs.
Yeah.
Yes. So you cannot feed a magic gnome into S. S takes strings.
I'm not using this argument, but
Okay.
I'm using the previous argument that we made, that we cannot, the diagonalization argument, that we cannot find that real number, which
Be careful when we say you cannot find the real number. Is perfectly well defined.
cannot be
computed algorithmically, but a magic creature can compute it. How? By magic. How does magic work? I don't have to explain it to you. It's a potion, it's a spell. A deity can do it too. See, that's one of the disturbing things about superstitions, and making arbitrary assertions about how the universe works, because you don't have to explain it. In fact, if somebody questions your religious explanation about the universe, it's almost heresy to question it. Right? It's not just not answerable; it's discouraged to be questioned. How does the magic of Harry Potter work? We're not going to tell you. We're not going to give you the equations when you wave a magic wand, exactly the physics of what happens. Because not only will suck the fun out of the movie, it'll be wrong, the explanation. We don't tell you how hyperdrive works, warp drive works in Star Trek, or lightsabers work in Star Wars, or time travel works in some other movies. Because it won't be so much fun, and it won't be possible to explain it using rational ideas and known mechanisms. So there can't be a magic gnome or a deity inside the box. They can, and if there is, they may be able to do the job. But what we're saying is that no algorithm can do the job. We're specific. Within algorithms, all bets are off. Within algorithms, saying that no possible algorithm could work in any possible language using any possible data structures or other subroutines or algorithms and so on and so on. That's still a very sweeping statement. That's saying that even a Google-sized algorithm with Google lines of code still couldn't do this job. Or any other algorithm of any size can't do the job still. That's a very sweeping statement. That's a non-existence proof. For proving we're not a millionaire. That's hard to do. Remember the last time we talked about millionaire versus not millionaire? It's not the exact symmetric opposite argument. One argument is easy, show me the money. One argument is very hard. Not showing you the money doesn't prove that I'm not a millionaire. So here we prove that we're not a millionaire. That's hard to do. We prove that not just one specific algorithm doesn't work, or one class of algorithms not. We prove that any algorithm cannot possibly work. That's a very, very tall order. Because we're talking about algorithms created by omniscient, omnipotent deities with an infinite wisdom, infinite intelligence, and even they can't write an algorithm to do the job because an algorithm doesn't exist to do the job. It's not the fault of the deity. This doesn't disparage, anybody's beliefs here. It's like saying there's no integer between a quarter and a third. And even a deity can't find one. It ain't there. Like an integer between a quarter and a third. And an algorithm to solve the halting problem ain't there either. And we just proved it. And that's subtle, and I've seen this for 40 years, and I still kind of get edgy and uncomfortable when I see it again, because it kind of rubs your intuition the wrong way. You think, an algorithm that's a Google-like lines of code should be able to do all sorts of amazing things, and yes, it will, but not this one, not this task, even though this task is pretty straightforward. There's a piece of code called. There'll be algorithms that can simulate human intelligence and even surpass human intelligence. We haven't found them yet, but they're there. They're not, don't exist. This supposed algorithm, this one doesn't exist. It ain't there. So that's different than super intelligent algorithm. Those we will eventually find. What will happen after that, for better or worse, is a different story. Maybe a better world and maybe Terminator, Judgment Day, but or something in between. But those algorithms exist, super intelligent algorithms. We just didn't write them down yet. This supposed algorithm doesn't even exist, much less being able to be written down. That's a very different story. Okay, questions?
Yeah. What if we have all the knowledge in the universe, so we are able to solve the halting problem, right?
No, of course not. If you have all the knowledge in the universe, can you find an integer between a quarter and a third? With all the wisdom possible, all the omniscience, omnipotence, you're a deity, you're a god. Can you find an integer between a quarter and a third with all your power?
No.
No. Why?
But the program can know that we can't find such an integer, so it can hold.
Because that integer isn't there. It's not your fault that with all your omnipotence and power and omniscience and infinite wisdom, you can't find an integer between a quarter and a third. It's not a disparaging statement about you, the deity. All it says is that integer isn't there to begin with. So you won't be able to find it no matter how much wisdom you have or power or omnipotence or billions of years to look for it. It ain't there. This algorithm ain't there either. We just proved it. It's deep, it's powerful, it covers a lot of ground, this argument. It's very dramatic. It's actually amazing that Turing was able to achieve this proof. This proof is not, but it's very subtle, and it's counterintuitive, and it kind of rubs you the wrong way, and it almost, it's almost annoying, or disturbing, I should say, that this would be true. Except that it happens to be true, this result. People have been trying to make end runs around this logic for, since 1935 when he came up with this, and 80 years later, there's no flaws in this argument. It's mathematically sound. In fact, it's so short that there's not a whole lot of places for truths to hide here. It's not like I gave you a 100-page proof and said, okay, Q with D, and you said, well, you know, I can even follow this long proof that's 100 pages, so who knows if it's true or not, or something bug in the, you know, that's not the case. This is a one slide, one paragraph, you know, kind of proof. There's not a lot of places here for truth to hide or falsity to you know, come and bite you. It's pretty. There's not a lot of moving parts here. Question.
Is there anything special about halting?
No,
In this?
no. We'll show later in the semester that almost every property, or non-trivial property of language is undecidable too. So not only there's lots and lots of other undecidable, algorithmically unsolvable problems, there's an infinite number of them. And not only there's a countable infinite number of them, there's an uncountable infinite number of them. And not only that, any trivial property of languages automatically is undecidable. We'll prove it. Theorem called Rice's theorem that will generalize the heck out of this and show you that almost anything else is undecidable. So this is not the exception. This is the pattern. This is the rule. It's amazing we can even add two numbers together. Because so many things are undecidable, uncomputable, algorithmically impossible to achieve. So this result by Turing is a very negative, very pessimistic result. Because it's true not just about the halting problem, but about lots and lots of other things. I'll give you a few examples. The problem of, I'll give you a program and you tell me if it's the minimum possible program that achieves the same input-output behavior. It's the smallest size program on the side. I give you a program and I say, does it print out prime numbers and prime numbers only on the side? I give you a program and say, does it print out anything or something? Nothing at all or anything at all on the side? And so on and so on and so on. And you can easily, on the heels of this, you can prove all these other results. And Rice's theorem proves an uncountable infinity of them all in one fell swoop. Right now we don't have enough machinery to do it, but soon we will. Now on the bright side, you know, a lot of things are computable. You can add two things together. Thank you very much. You can multiply matrices. Okay. You can have a program that'll play World of Warcraft. Okay, cool. So not everything is undoable. Some pretty sophisticated things are doable. You can have a program that allows you to share, you know, photographs and you know, tweet people and paste things on people's walls and watch their. It's called Facebook. You may have heard of it. There's a program that allows you to search other people's computers. It's called Google. Possible, but an uncountable number of things are impossible. Only a countable number of things are possible. How do we know there's only a countable number of things are possible? Algorithmically compute or achieve. Yeah. The other one. Dovetailing. Yeah. If you answer to any question I ask you is either dovetailing or diagonalization, you know, most of the time you'd be right. That's how much mileage we'll get out of these two concepts. That's why I introduced that's why I just skipped the canter before we talked about anything else. And what do we mean by dovetailing? Because you know, number all the programs. There's a countable number of them. But there's an uncountable number of functions, even Boolean functions. How do we know that? Uncountable number of Boolean functions. Diagonalization. That's the other one. And what was the proof for that? Well, you know, that was the proof right there. And these are just Boolean functions. Most functions are not Boolean. Most functions have arbitrary output, not just 0, 1. So there's even more of those. But even the Boolean functions are an uncountable number of uncomputable and undecidable functions. Okay, a few more subtle issues. Is there any more questions yet so far? I'm going to go into a few more subtleties here about the halting problem. So, by the way, fed T to itself, right? T was fed to itself here. When do you ever want to feed T to itself in real life? You actually have scenarios where you actually want to do that. Give a program to itself.
Create a mechanism.
Recursive. Well, recursion is when it calls itself, not when it's fed to input. Two different things. I mean, if you take a Sudoku program and feed the Sudoku program to itself as input, I'm not sure it'll probably blow up. I'm not sure what it'll do, but it's a little bit unnatural there. But when is it natural to feed something to itself?
When you create the next version of the compiler, you use the previous version of it.
So if you create a new compiler, say for C++, and you create a super duper optimized compiler that runs faster and produces more optimized code, more efficient code. But, you know, a compiler produces inefficient code or efficient code based on how much optimization they do internally. It takes longer to produce more efficient code and so on. You create a super duper new compiler for C++. Could you write it in C++? So what would compile it? The previous C++ compiler will compile the new compiler. So you feed the old compiler, you feed the new compiler to the old compiler. But you don't stop there. Because now the old compiler produces an executable of the new compiler, but it's not optimized according to the new compiler. It's optimized according to the old compiler. But now it's compiled. The new compiler is compiled. What do you do next? Feed the new compiler now to itself, which produces a new version of the new compiler that's optimized by the new compiler, which produces better code, more efficient code. And you just fed a program to itself in a very practical situation, and it will do exactly that. It happens in the industry all the time. So I want you to know that feeding something to itself is not just something weird that we do for the purposes of this proof. It happens in real life. In practical situations, you want to do that. That's what I'm saying there. Okay. More subtleties. So basically the bottom line is that infinite loops are arbitrarily hard to predict. How many had infinite loops in your code at some point when you were debugging in your entire life? How many ran into infinite loops? Okay. Now you know why they appear so often. It's very hard to prevent them from appearing. It's very hard to determine if a piece of code will run forever or not, and often it runs forever inadvertently, and it's very hard for you to tell when this will happen or why it happens when it does happen. And it's hard to debug infinite loops. In fact, it's undecidable. It's incomputable algorithmically to determine an infinite loop. So, here, now we can, this is the argument here, that there are numbers that are finitely describable but not computable, right? So this is the argument here. I'm going to take all these digits and make them solutions to the halting problem on P and I, and I'm going to represent each P and I as a single integer by representing it as 2 to the P, 3 to the I, as a single, and use that as the index into these digits. So each digit here will represent a P and an I in this form. Why do I say 2 to the P and 3 to the I? I could have said 5 to the P and 7 to the I, but I could not have said to the P and 4 to the I. Why? Unique factorization, right? If these two are prime numbers, from the value 2 to the P, 3 to the I can uniquely determine P and I. How many understand that? Okay. So now I'm going to make these digits solutions to the halting problems for these PI combinations and make this digit 0 if P holds on I, and make it 1 if it doesn't hold on I. And now this number, which is between 0 and 1, is a real number that I completely described and described it finitely, because I just stopped and that's the description. I just gave it to you. But it's not algorithmically computable, because if it was, I can use the subroutine that computes digits of this and use it to solve the halting problem by calling that subroutine. How? I call that subroutine for successive digits. When I get the right digit for my PI combination, that digit will tell me if that PI combination will halt or not halt. And that will be an algorithmic solution to the halting problem. How many understand this argument? Okay. You gotta think about it some more. I'll leave this with you to think about. So I just gave you a real number that's finitely describable, but not computable. Okay, so I fulfill this promise to show you an example of one of these in red. Finitely describable, real number that's not computable. There's no algorithm to compute its digits. Okay, a few more subtleties. What the unsolvability of the halting problem means is no single algorithm that by itself solves all input combinations program input combinations for halting or not halting, it always stops and is always correct. Not a single algorithm. It doesn't mean that if you allow incorrectness, remember that course, if you allow the algorithm to be wrong sometimes, of course it's a very simple algorithm that will determine halting or not halting if it's sometimes allowed to be wrong.
Say always yes.
Always say yes, for example, in such an algorithm. You give me an instance of the halting problem, I'll always say yes. Sometimes I'll be right, sometimes I'll be wrong. And saying yes is a very simple algorithm. One line of code, print, quote, yes, unquote, stop. That's the algorithm. How many get that? Good. That's like saying a clock that stopped is correct twice a day. It's incorrect many other times a day, but it's still correct twice a day. It's not always wrong. How many understand that? But that's not saying much. If you allow incorrectness, a clock could have a very simple mechanism. Just draw two hands on the wall with chalk and that's your clock. And it'd be correct twice a day, regardless of where you put your two hands. And that's not a very sophisticated clock and it's not a very useful clock. So an algorithm that's allowed incorrectness in some instances is for the same reason as the clock that stopped. Is not useful and not very correct and not very practical and not very sophisticated and it's not saying much. So all bets are off if you allow incorrectness. But if you allow incorrectness, you have much bigger problems than halting not being algorithmically solvable. You have a clock that stopped, basically. Okay? Now, if you allow infinitely large programs, all bets are off again. By the way, what is an infinitely large program? Can you have an infinitely large program in C? How many say you can? You cannot. Why can't you have an infinitely large program in C?
Because you know that you need a closing parenthesis.
You need a closed brace to the open brace. But if the program was infinitely large, not only there won't be a brace at the end, there won't even be an end of any other kind besides a brace. So you cannot have an infinitely large program in C or any other language. Now, you may be able to define a new language that may have infinite programs, but it won't be C, and an infinite program will not be describable finitely even in this new language. Because if you could describe an infinite program finitely, you'd have a finite description of numbers that cannot be described finitely, and that would be contradiction also. So even if you allow infinite programs, they can still not be described finitely, and you'll never know what they are. And you can't even have infinite programs because, for example, C needs a closed brace, which will not be there in an infinite program. So the result that we just showed a couple slides ago, the halting problem proof, doesn't hold when you have infinitely large programs. Or if you have an infinite number of algorithms, each one should solve a different instance of it. That's equivalent to an infinite program. Right? You can think about an infinite if statement. If the input is 1, then print 1. If the input is 2, then print 1. If the input is 3, then print 0. If, then, else, if, then, an infinite string of if, then, else's. That's an infinite program. You can't have that. That's not an algorithm. And you won't be able to construct that if statement from a finite description. Because if you could, the halting problem would be solved algorithmically from that finite description. And that's a contradiction. And if you have an infinite number of separate algorithms, that's equivalent to having one infinite algorithm. A finite, an infinite number of finite algorithms equivalent together to an infinite algorithm. So that's not, and the result doesn't hold in this scenario. Okay.